Okay, sincerely apologize earlier. I think my computer hang. My bad. So where I last stopped is we talked about the reaction at point C, right? So this is the reaction that we get at point C, where now, right, we not just have the moment at point C. Oh, okay, we not just have the moment. We also had the. This is something weird. Sorry. So we have the moment, and also we have a force. We have two things acting at point C, inducing failure now. Okay, so now when that's the case, the stress is still in the x direction, right? So stress in the x direction now, we have an extra term. So we have the force in the x direction. So this F is also, I call it Px, okay, divided by area, right? So this, for this case, this is due to the what? Excuse me, axial loading. And then the next term over there, what we have is mz. So moment will be acting on the z-axis, divided by izz multiplied by y. Okay, so this is due to the bending moment. Okay, so for this case, what we see over here, this is equal to plus, okay, and this is also equal to plus. For this case, I just put both plus, but what I want you to focus on is this. I don't want you all, so I'm going to put down here. When I put circle over here, okay. So it's not always plus. So you need to analyze whether is it positive or negative. And the analysis is based on compression tension. So this is the moment vector, right? You see over here is a moment vector. And then later on, I'll show you example, okay, whether is it plus or minus, okay. But the root formula is you have to consider the axial load and the bending moment. And important thing to take note is mz over here is p prime multiplied by d, okay. Now, I'll break things down for you so you understand what I mean by don't worry about the sign, okay? Like before, like last week, I think I also emphasized that do not worry about the sign. I want you to visualize what the moment is doing. That's more important than worrying about the sign. Okay, so let's look at one condition. Okay, let's look at one condition over here. So the condition will be exactly the same as in the problem. Okay, so I'm going to sketch this out. Right. So this is the axis symmetry part. So that's the other half. So basically, I'm trying to sketch this. I'll simplify the sketch to be like this. Right. So this is where we have our over here on the diagram. This is our point C. Right. And then we have a force moving down here, known as P. Okay. And then the distance from P. Okay, so the distance from P, I'm going to do something different now here, right? So the distance from P, so the distance from here to here is D. Okay, so you see where D touches. D and the D up here are not the same, yeah? The D over here, it go up to the centroid. Okay, so my D is over there, right? And then the distance of my centroid, I'm going to call it E. Okay, so E is the distance of the centroid. because later on you have to find the centroid. Okay. So for this case, we know that the moment, right? The moment in Z. So this is our transformation. X, Y, and this is rotation in a Z. And we know if C, this is our reference point, or I will not call it reference, this is our fixed point. All right. We're going to have a moment in this direction. So moment in Z. So now the top is known as compression, and the bottom is known as tensile relative to the centroid. Okay. So now I'm going to have 2 extra points. Okay. So this is alpha at the top is my point alpha. At the bottom is my point beta. Okay. So if we are to sketch out our reaction, so our reaction we will have at point P, we have a reaction that is known as P in the X direction. And then the moment, right? So this is moment in the Z direction at point C. That's the counter moment. Okay, action equal reaction, Newton's third law. So from here, right, we are going to calculate the stress. Okay, we're going to calculate the stress, right? X, all right? So all the stress we were calculating is in the X direction, normal stress direction, X, okay? And then at alpha, right? So we can see that from here, the PX is going to induce a what? Tensile, yes or no? Because it's pulling away from point C, or the surface at C. So it's plus by PX divided by A. So where is A? Okay, so A is over here. So A is the cross-sectional area. Okay. And then over here, the moment now, right? So you have the moment now we know is equal to mz over izz multiplied by y. And the moment at point alpha, I want you to focus on alpha, right? We're looking at point alpha, it's going to be under what? Compression. So that's where you put a minus down here. Okay. So this is 1. And then if you look at point X, okay, sorry, stress X at point beta. Okay, so beta over here is down here. Okay, so at beta, Px is still inducing a what? A tensile. Okay, so this is still equal to plus by Px divided by A. And then at beta down here, below the centroid, right? At beta, we know from the moment arrow, we are going to see a what? A tensile. Okay, so this is where it is plus mz over izz multiplied by y. I want you to visualize this, not just to plug in the formula. So you can see whether it's plus or minus is based on what? The moment arrow. I don't want you to like, oh, that's why over here, all right, I will emphasize over here, what I'll do is, don't worry, or the sign is based on what? Analysis of the moment vector. Okay. See, sorry. So one is based on moment vector. So this one is based on axial loading vector. Okay. So I don't want you to like memorize this sign and don't know why this is plus or minus. Okay. So you have to be really careful. Now, so the next thing that I want to do now is we are going to sketch. Okay. We're going to sketch the stress distribution now. Okay. So let's just assume. Okay. Let's just assume the cross-sectional area of this structure. Okay. Let's just assume the cross-sectional area of this structure is like this. Okay, it's rectangular. Okay, so I'm going to draw bigger. Okay, so this is the cross-sectional area. So cross-sectional area, right, relative to this transformation that we have, right? So where we are viewing now is we are viewing at point C. So this is our transformation now. So this is our Z, Y, and then this is our rotation about X, and the top is what we call our point alpha, and the bottom is where our point beta. Okay. So now, based on the cross section, right? This is by observation, right? This is the centroid, right? This is the centroid, right? So we're now going to sketch. Okay, now I'm going to sketch the stress view now. Okay. So I'm going to change the view. So when I sketch, I know. Okay. I'm going to shift this a bit. Okay. So we're going to sketch the stress view now. And I'm going to be sure that we use about the same. Okay. So now, this is our stress in the X direction. This is our Y, right? So the first one we're going to sketch is equal to stress X is equal to PX divided by A. So it's going to be a constant. Okay, so we're going to sketch this. This is going to be a constant. Right, not arrow. Right? Okay. So this value over here is equal to Px over A. So this is tension. Okay, so this is our tension. Now the bending moment now, right? So this is positive, right? Because over here is 0. Okay. Now our bending moment now, right? On alpha and beta. So 8, 4, 4, 8. Right. So now I'm going to. I'll be so annoyed if this thing hang. Second time, you know. And how come I can get a star over there? Sorry. So the next thing that we draw is our stress view for bending moment, right? So now this is our Y. This is our stress X. And we're going to plot stress X is equal to my over I. Okay. So what you see over there, so the top part is your alpha point, right? Bottom part is your beta point, right? So this is also beta, and this is alpha. So what we'll see is we have, based on this loading condition, alpha is in compression and then beta is in tension. So our moment, this is just purely moment. I elaborate again, this is purely moment. You have a stress view looking this way. Okay. This is so weird. Yep. Let me draw this better. Because if I don't draw it well, it'll be confusing. Okay, so this is our, so we have compression. So compression means it's pushing towards the structure. Tension means it's pulling away from the structure.